Okay, so let's start today's lecture. And before we start, any questions on what we covered last time? Last time we covered convolution, tabular method or flip and shift method, did certain examples and also showed that the same thing can be applied to some extent for continuous time systems also. So that is what we covered last time. So before we start today's lecture, any questions on what we covered last time? So if there are no questions, then let's just start today's topic. And today we'll be starting slide set number 7. We have finished up till slide set number 6. So let's just continue with this. Okay. So in this slide set, it is slightly new concept that we'll be covering. And this will be the concept of eigenfunction and eigenvalues, and also basis functions related to that, and Fourier series. Now what all we will be covering, it's all given right here. So we'll be introducing Fourier series, but we'll be using the concept of eigenfunctions for that introduction. And we will show that how this eigenfunction concept helps us in finding solutions or finding outputs for any given system. And obviously introduction to signal basis functions all will form part of this lecture. So what all topics are covered from signal system, Wapner-Wilsky? For those of you who are covering or sort of following the MIT courseware, it is basically lecture 5 from there. Okay, so let's introduce the concept of eigenfunction. So what is an eigenfunction? An eigenfunction, as we engineers take it, is a function which, if given as an input, let's say that phi kt is an eigenfunction. Phi kt is an eigenfunction. If we give this eigenfunction as an input to our system, the output of the system would be the same eigenfunction multiplied by something. Now this something is known as the eigenvalue. So this is the property of eigenfunction. If you give it as an input to any system, I should just qualify this to an LTI system, then the output that comes out is the same function multiplied by something, some multiplicative factor with that. So this function gets modified by this multiplicative factor, and this multiplicative factor, or the thing that gets multiplied with eigenfunction, is known as the eigenvalue of that eigenfunction. Now let me again clarify one more thing. Mathematicians see function differently, and we engineers use this name function synonymously with signal also. So whether we call it an eigenfunction or eigensignal, for example, this cosine t, for mathematician this is a function. It's a function of time, it's a function. For engineers, this is a signal, and we can plot this signal against your time axis t. So the use of this term function and signal should not confuse you. I will be just using this thing interchangeably, at times calling it a function, at times calling it a signal. It's one and the same thing. And that is true also for different books written and whatever site you will follow. So this term signal and function at times are used synonymously. So an eigenfunction or an eigensignal is something which, if given as an input to a system, the output would be the same thing modified by some multiplicative factor, and that multiplicative factor is known as the eigenvalue of that particular eigenfunction. And notice we have this subscript k. So you may have not one but multiple of these. Phi t's, you may have phi 1t, phi 2t. So it is not that you will have just one eigenfunction, you may have a whole series of eigenfunction, and each will have its own eigenvalue. And similarly, we can have 2, 3, 4, whatever. So we can have multiple of these eigenfunctions, and these eigenfunction have this property that if you give that as an input, the output would be the same eigenfunction multiplied by its eigenvalue. The use of this particular concept, how this is useful for us, how the eigenfunction is useful for us, it will be very useful if we can somehow represent our input signal in terms of eigenfunction, in terms of scaled sum of eigenfunctions. So if we can somehow do this, some scaling factor phi 1t plus some scaling factor phi 2t. If we can do this, then this whole eigenfunction thing becomes very useful for us, because then the output would be, for each eigenfunction, the output would be its eigenfunction multiplied by the eigenvalue. So then to find output, all we need to know is what are the eigenvalues for those eigenfunctions. We need to know these lambdas. So this is the whole beauty of this concept, that if we have eigenfunctions and we know the eigenvalues of those eigenfunctions, then further, if we can represent our input signal, if we can represent our input signal in terms of sum of those eigenfunctions with some scaling factor, then we can find out output, and output would be sum of the same scaling factor multiplied by eigenvalues and multiplied by eigenfunction. So output can be easily computed for that given input. If input is this, output would be this. That's the concept of eigenfunction and eigenvalue. Now there are few assumptions here. Rather, I will say there are two assumptions here. First assumption is that we know your eigenfunctions also, and we know the eigenvalues of those eigenfunctions also. First assumption. And the second assumption is we can represent x of t, or we can break up x of t in terms of eigenfunctions, in terms of your scaled eigenfunctions. So these are the two assumptions which are present here. If we can somehow find out eigenfunctions and eigenvalues, and also show that those eigenfunctions can be used to represent your input signal, then this whole concept is very strong and very useful concept for us. So anybody having any confusions as far as the concept of eigenfunction? So very straightforward concept, that an eigenfunction is a function which, if given as an input, the output would be your eigenfunction multiplied by its eigenvalue. Okay, now for us, eigenfunction, not one but a whole series of eigenfunctions, were identified by one very famous, you can say, mathematician or scientist by the name of Laplace. He was one, you can say, mathematician or scientist who showed that e raised to the power of st is an eigenfunction for an LTI system. And here S is any complex number. S is a member of a complex number. So this is not one eigenfunction, this is a whole series of eigenfunction, because we can just have any complex number here, and that complex exponential that results would be an eigenfunction. So we can have a whole infinite numbers of eigenfunctions. Just put this thing as 1 plus 2j, so that is one eigenfunction. or 2 plus 8 minus plus whatever. So you will keep getting different complex exponential, and each of them, as long as s is a complex number, would be this complex exponential would be an eigenfunction. And that also shows that why we were emphasizing so much on complex exponentials. So this is one thing that was given to us by one particular scientist by the name of Laplace. He showed that e raised to the power of st is a eigenfunction. So we will see that we'll prove first that yes, it is an eigenfunction. And to prove that, we have to show that if we give that e raised to the power of st as an input, the output should be the same e raised to the power of st multiplied by something. And that something would end up becoming the eigenfunction. Okay, so let's see what we have next. I will come back to this Fourier theory in a few moments. Okay, so here we were, eigenfunction. Now, if we can somehow have eigenfunctions which are also basis functions or signals, then would be the real use of these eigenfunctions. And what are basis functions or basis signals? We have already discussed it earlier. A basis function or basis signals are those which can be used as building block. So if you have basis signals, then we can have multiple of those basis signals, combine them and make more complex signals. So they can be used as building block. Or in other words, any complex signal can be broken up, or you can say represented by these basis signals. So we have to first of all see that what all basis functions can be eigenfunctions, or somehow identify eigenfunctions which can be used as basis functions. And if we can do that, then if input, we know what is eigenfunction. Input of eigenfunction to a system results in that eigenfunction multiplied by its eigenvalue. So the output for an eigenfunction or signal is same as the input multiplied by some constant or some factor lambda. So here notice that we are using the term signal instead of function. So if we can represent your x of t as sum of scaled eigenfunction, the output would be sum of scaled eigenfunctions multiplied by its eigenvalue. And again, as I mentioned, two basically things are very important right here in order for us to be able to use this concept of eigenfunction. First of all, identifying eigenfunctions and their eigenvalues. So this is the first factor which is important. We are calling it here as system identification. So we have to somehow come up with eigenfunctions and find out what are the eigenvalues for those eigenfunctions. Second, we also have to have some way in which we can represent your input x of t in terms of scaled eigenfunctions. And these scaling factor, we have to have some way of computing these scaling factors. These scaling factors. So we have to have some way of actually representing your input signal x of t in terms of scaled sum of eigenfunctions. And we need to have some way of finding out what all scaling factors ak would be. So this concept of eigenfunction and eigenvalues is to some extent similar to matrix decomposition, the concept which is used there in matrices for eigenvectors and eigenvalues. But again, that is mathematics. Here we'll see that how we use it here in signal system. So let's come to this very concept of eigenfunction. We said that if we have your system, LTI system, continuous time LTI system, xt input, yt output, with any impulse response h of t. Now, in order to prove that e raised to the power of st is an eigenfunction, let's see that if we give that as an input, what comes out. If what comes out is the same e raised to the power of st multiplied by something, then it would have been proven that e raised to the power of st is an eigenfunction. Now the output, we know y of t is basically convolution of uh, x of t with h of t, and again the property of convolution, order doesn't matter, you can take anyone first, anyone next, doesn't matter. And convolution is basically convolution integral for continuous time. So this is basically h of tau x of t minus tau. So we already know this. Now if we give the input as e raised to the power of st, then this convolution integral comes out to be e raised to the power of st minus tau. So if xt is this, x of t minus tau would be this. So this will be the output that we get if we give e raised to the power of st as an input to any system with impulse response h of t. Output would be this. Now this we can break up in two parts. So we can just write it as minus infinity to infinity h of tau e raised to the power of minus s tau multiplied by e raised to the power of st d tau. So two parts, we can just break it as this. Now in this e raised to the power of st is constant as far as tau is concerned, because this term doesn't have any tau there, so we can just take this term out from the integral and we end up getting what? Minus infinity to infinity h of tau e raised to the power of minus s tau d tau, and e raised to the power of st goes out. You can write it on this side, or we can just this thing multiplied by e raised to the power of st. So notice what we ended up getting. So the input given was e raised to the power of st, that was the input, and output that came out was the same e raised to the power of st multiplied by something, and this something has been given a particular name. This is known as, or this is given the symbol of h of s. So the output that we get came out to be this. So this actually proves that your e raised to the power of st is an eigenfunction, because once we gave that as an input, the output that came out was same e raised to the power of st multiplied by something, and that something we gave it the symbol h of s, because this will be some function of s. This h of s that we get, which we have labeled as, which we have found out to be h of tau e raised to the power of minus s tau d tau, this thing is basically the eigenvalue for this e raised to the power of st, and as I mentioned, e raised to the power of st was the eigenfunction which was given to us by Laplace, the scientist named Laplace, and s is a complex number. And this h of s, if you see here, this is basically integral of the product of h of t with e raised to the power of st. So whether you write it as h of tau, whether you write it as h of t, doesn't really matter, it's just going to give you the same result. So one and the same thing. So this thing in mathematics you have already covered and seen this thing, and this is basically Laplace transform. You have been doing this Laplace transform in your mathematics, but here we have a different view of this. So this h of s is nothing but integral of your impulse response with your input, integrated for minus infinity to infinity. So this is your eigenvalue, and we called it as h of s. So we actually proved that e raised to the power of st is a eigenfunction. So this concept of eigenfunction and eigenvalue, you will see, is very useful for us. So any questions here? Arsalan, I can see your mic on. Any question? Anybody, any question? Okay, so let's just continue with this thing. So this concept of eigenfunction and eigenvalue is very useful. Now, how is this useful for us? Without further, you can say, complexity, let's go through it. So this is already covered in the slide, whatever we showed on blank screen. So we showed that if input is e raised to power of st, where s is any complex number, we found that output came out to be your h of s multiplied by e raised to power of st. Therefore, e raised to power of st is a eigenfunction and its eigenvalue is h of s. Let's see a simple example of how we can actually use this. So here is a simple system. It's a very simple pure time shift system, as we say. This is a pure time shift system in which input is x of t and output would be just a shifted version of that. So a very simple time shift system. Let me do it separately here. So let's do a simple example and see that how this concept of eigenfunction and eigenvalue can really help us. So for this example, we have a continuous time system and the difference equation for this system is given to us. It is given to us that y of t is equal to x of t minus 3. So this is basically given to us already. Just give me about a minute. Let's take about a minute break. Okay, so this was a simple example given to us. And let's see that how this concept of eigenfunction can really help us here. So in this, we were actually not given h of t. And it was said that the input is, let's say, x of t is equal to, if x of t is equal to e raised to power of minus j2, then what would be the output? Minus j2t. So this was the input, this was the system, and we were supposed to know that we were supposed to find out what is the output. Now this is a very simple system. We can directly find out the output also, because if x of t is this, it's a very straightforward system. The output y of t would be just shifted version. It would be e raised to power of minus j2 into t minus 3. We can simply do this and simply find out the answer for this, or in other words, we can write it as e raised to power of minus, we can just divide it into two parts also. It is basically minus j2t and e raised to power of minus 6j. So minus 6j or plus 6j, it is basically j6 into e raised to power of minus j2t. So whatever way we want to write it. So this was a very simple system. We could have found out answer directly also. But let's just use the concept of eigenfunction and eigenvalue. Now we know that eigenvalue is basically going to be h of s, which is going to be integral minus infinity to infinity h of tau e raised to power of minus s tau d tau. And here h of t we can find. This is a simple feed-forward type of a system, FIR system, so we can directly write h of t replacing x with delta. This will give you delta t minus 3. This is your h of t. So using that, we know that if input is delta t, output is h of t. That's already known to us. So if we replace x with delta, y becomes h. So from here we can really find out delta t minus 3 is basically h of t, and from here we can just plug the value here, minus infinity to infinity, it will become delta tau minus 3 into e raised to power of minus s tau d tau. And we can directly write the answer here. H of s comes out to be equal to e raised to power of minus s minus 3s or minus s3. So this is your h of s. Now how can we directly write answer? We already showed this, that if inside an integral you have a delta, then we can directly write the answer, because we have to integrate this product over this entire range of tau from minus infinity to infinity. This product has to be evaluated over this entire range. But we know that this product, this particular term here, will be 0 throughout. It will be 1 only at tau equal to 3. So if you see this h of, we should be comfortable in this concept by now. So this is your delta tau minus, let's call it tau or t minus 3. If it is tau axis, it will be tau. If it is t axis, it will be t. So this is your delta tau minus 3, 0 throughout, 1 only at tau equal to 3. So this term will be having value 1 only at tau equal to 3, and rest it will be 0 throughout. So this product over the entire range will be throughout 0, and it will have value equal to 1 into minus 3s. That's all. So we can directly write single value here, 1 multiplied by e to the power minus 3s. So integrating with a delta function is very straightforward. We can directly write answer. So this is h of s. So the way this eigenvalue concept is used is, the first thing we need to do is we need to find out your eigenvalue h of s, which is a Laplace transform of h of t, or just this integral h of tau is by minus s tau d tau. Plugging in value for this h of tau, we can directly find out what is h of s. Now we know h of s. So the concept of h of s is, if input is e raised to power of st, output is h of s times e raised to power of st. Simple. And we have found h of s. In this question, if you see, the input given to us is e raised to power of minus 2 times t. So s, or complex number, is minus 2. So if x is e raised to power of minus j2 times t, the output y would be, y of t would be equal to, as we mentioned, h of s into e raised to power of st, and here instead of s we have j2 or minus j2. So e raised to power of minus j2 times t. So h of s is this, h of minus j2, replace it with minus j2, we will end up getting e raised to power of minus 3 into minus 2 makes it plus. So 6j into e raised to power of minus j2t. And we can combine it together and write it as this also, e raised to power of minus j2t minus 3. It's up to us how we write it. So if you see this, this is same as this right here. So a very straightforward concept. It is just that we need to find your h of s, and then output would be just this. So if input is eigenfunction, output is eigenfunction by its eigenvalue. We need to know the eigenvalue. In this question, the input was again a complex exponential. Complex exponential are eigenfunctions. We have already seen this. And in this complex exponential, s was minus j2. So we need to find h of s. H of s came out to be e raised to power of minus 3s. So output is basically, for e raised to power of st input, output is h of s e raised to power of st. So if we replace s with minus j2, output comes out to be something like this. So very straightforward concept that we are going to use right here. Any confusions here? Okay. So the same thing is actually covered right here. So if we are given a pure time shift system which has difference equation given to us, and if input is this, e raised to power of j2. So example I did was for e raised to power of minus j2. So one the same thing, you can just have this example here. So if input is e raised to power of j2, we can directly find the answer but just by replacing xt with e raised to power of j2t. Output can be directly found out to be equal to this, and this is for plus j2t. Output is this. Now we need to find your h of s. So how do we find h of s? First of all, we find impulse response comes out to be delta t minus 3. The system impulse response we see here is delta t minus 3. It was not given, we derived it. How did we derive it? Because this was your system. So if x is replaced by delta, y becomes h. So h of t becomes delta t minus 3. And then we can find h of s, which is going to be integral of h of tau e to the power of minus s tau d tau, replace h of tau, and we end up getting the answer directly. How can we write the answer directly? This product we have to evaluate over the entire range of tau from minus infinity to infinity. Now this particular term has value 1 only at tau equal to 3, and rest all values of tau will give this term as 0, so this product will be 0. So if we have to evaluate the whole thing, this product over the entire range, only one point will have value, and that point would be where tau is equal to 3. At tau equal to 3, this is 1, and this is e raised to the power of minus s into 3. So that's simple answer. So this concept of having a delta inside a summation or integration, be comfortable with this. You should have already known it from your mathematics, but if you don't, then this is how it will be useful. As an engineer, always try to simplify things. As I keep repeating in my earlier lectures also, we as an engineer have to engineer the simplest possible solution to a problem given to us. So in this particular case also, that's what we try to do. This integral, we can directly write the answer. So h of s is e raised to the power of minus 3s. Now the output, if you want to find out the output is going to be just y of t is going to be your h of s into e raised to the power of st, if input was e raised to the power of st. In our given example, h of s is this, and s in our case, in the given case, is j2. So e raised to the power of j2t was given to us, so e raised to the power of j2 times t into h of j2. This is what we need to evaluate, and just plug in the value, you will end up getting the value right here. hj2 is this, so you end up getting this hj2 into e raised to the power of j2t. So this whole thing is basically here. So simple example was shown where we showed that how this concept of eigenfunction and eigenvalue can be used to solve very simple systems. Now let's do the same example just by changing the input. Let's keep the same system and let's just change the input to this system. If we keep the same system, then your h of s remains the same because that is dependent on your system. So it is e raised to the power of minus 3s. So for the same system, if x of t is changed, now let's take a cosine, the next example. For the same system, if we take input as cosine 2t, if we have x of t which is equal to cosine 2t, and we have already seen for that system our h of s was equal to e raised to the power of minus 3s, I believe. So if we have input as cosine 2t, what we need to do is first of all break this x of t in terms of complex exponentials, and Euler actually showed us, or what? So we can really simply break it up into complex exponentials, and it will be e raised to the power of j2t plus e raised to the power of minus j2t and half outside. So this is going to be your complex exponential representation of cosine. And complex exponentials are of the type e raised to the power of st. So if input is e raised to the power of st, output is e raised to the power of st into h of s. And here s is j2, here s is minus j2. So for this, the output would be this, the same e raised to the power of j2t into h of j2. H of j2 is e raised to the power of minus j6. And similarly for this, the output would be this. And the scaling factor gets multiplied. So this is how we actually solve this. So for cosine, we break it up. We can directly find out the answer because these are your h of s for different s values. And then you can just rearrange and write it as this way. And if you have two complex exponentials which are conjugate of each other, we know that they can be represented as a cosine. So we can just represent the whole thing as a cosine. So cosine 2t minus 3. This will be your output y of t. So the concept is very straightforward. We have complex exponentials which are eigenfunctions. We just need to know the eigenvalue for those eigenfunctions. Any confusions here? So let's just extend this, and if we have multiple cosines given to us, same system, if we have cosine 4t plus cosine 7t given to us, and remember that your h of s for that system was e raised to the power of minus 3s. So if input given is this way, again the same thing, we need to represent that cosines in terms of complex exponential. The first one would be this, the second cosine would be this. So first of all, represent it in terms of complex exponentials because complex exponentials are basically eigenfunctions. And once we do that, we know that these are complex exponential of the type e raised to the power of st. And we have 4 of these with different s values. And we know that h of s is e raised to the power of minus 3s. So this one will give you the same thing into h of j4. Just replace s with j4, you'll end up getting this. So we have h of s e raised to the power of st throughout for each term. This is basically your answer. Then we can just combine the exponentials together and rewrite it like that. And if we have complex exponentials which are conjugate of each other, they can be represented as cosine. So we can just represent it as cosine. Output directly comes out to be equal to this. So for the same simple system, pure time shift systems, we saw that if we have different inputs given to us, and specifically we stuck to complex exponentials or sinusoids, and sinusoids can be represented as complex exponentials. So in case of sinusoids, it was very simple for us to use this concept of eigenfunction and eigenvalue. So this eigenvalue was computed for the system, and notice that this eigenvalue h of s is actually property of your system. So it is basically your h of tau e raised to the power of minus s tau d tau, and it is basically going to be function of s. The result that you get for this h of s would be some function of s, and this will be the property of that system. And if you know h of s, then we can find out output for any particular eigenfunctions because we know the eigenvalue. And eigenfunctions, if they are of the type e raised to the power of st, output would be e raised to the power of st multiplied by h of s. So this was the concept of eigenfunction and eigenvalue, and in this particular lecture we just stuck to one particular set of eigenfunctions which was given to us by Laplace, and that was complex exponential of the type e raised to power of st, where s was any complex number. And Laplace actually showed that your e raised to power of st eigenfunctions eigenvalue would be Laplace transform of h of t, or in other words, integral minus infinity to infinity h of tau e raised to power of minus s tau deta. So this was what we had for today's lecture. And again, in tomorrow's lecture, we'll be finishing this slide set